let's go into the history and develop the intuition and theory for transformers and attention layers. Historically, attention layers were introduced in 2014, and they were introduced for RNNs, in particular LSTM. So the authors of the original paper looked at the task of machine translation. So if we want to translate a piece of text from English to French, for each word YT that we want to predict and translate, the authors said we can create vectors called A's or attentions that will determine how much the model should pay attention to X1, the first word in the input, 2, 3, all the way to XT. So these are different weights that determine the amount of attention. So if we want to pay some attention to the first word, a lot of attention to the second word, and no attention to the other words, the model will learn how much attention it should pay. So if we zoom in what an RNN is, it's basically a probability, a conditional probability that determines probability of YT, prediction at time t, as a function of previous Y's that were generated, plus a single context vector. That's basically LSTM. We can write this as a function g of the previous word, hidden states, and this single context vector. So that's a traditional RNN. But the paper introduced was a layer called self-attention, which basically replaces this single context vector into multiple context vectors. So instead of having one context vector going into the prediction of YT, we'll have T context vector for each input word going to the prediction for a given output word. So if we have T prime outputs, the number of CIs would be T times T prime. So that kind of makes it computationally more challenging because we have quadratically more parameters to train. And to calculate the value of AT, we would basically take the softmax to make it between 0 and 1, and then multiply by the hidden states. And this would determine if it's 0.1, should pay 0.1 attention to the hidden state at point J. If it's a large value like 0.9, it should pay more attention to 8J. So that's the concept of attentions. In the same paper, the authors looked at the task of translating from English to French and looked at those different values of alpha for each prediction. If you look at the plot, we'll see for the word économique, attention is paid to European economic, and this kind of intuitively makes sense. Even us as humans, if you want to translate from a language that uses adjectives before nouns like English, European economic, to a language that does the opposite, creates a noun and then the adjective, we have to pay attention to both words. So that shows the intuition behind attention layers, which word it should focus on to predict the next word. So the combination of attentions and RNNs were not developed since then, and the reason is the computational limits and costs associated with RNNs. They are very costly because each operation is sequential. Every hidden state from the previous step needs to be calculated for the next output and hidden state to be calculated. So the sequential nature is kind of antithesis to the idea of AI, where we want to have parallelizable operations that we can pass into GPUs and have them performed really fast. Also, since we want to retain the computation graph of going from H1 to 2 all the way to HT. This backpropagation through time becomes extremely costly because we have to keep track of every multiplication between hidden states so that during backpropagation we would be able to calculate the gradients, and that's really costly. And plus adding this t times t primes number of parameters also makes it even costlier. So RNNs were discontinued and attentions were developed as a standalone set of layers. The challenge here was to capture the dependencies between words. RNNs did a good job with that by having a hidden state that would input to the next word. But here we need to find an alternative way to capture word dependencies, and we see from the Transformers paper how it's done.